Good morning, everyone. Maria, can you hear me?
Yeah, I can hear you.
Okay, good. Hopefully that means everybody can hear me. So one announcement, office hours will be held over Zoom instead of in person. And so Maria is going to post a document with a list of Zoom links for both lectures and office hours. So please use that document. It'll be posted on the B-Courses website. Please use that to if you want to ask questions and attend office hours. All right, so last time we finished up our discussion of, again, let me remind you, if you have a question during the lecture, please, you could raise your hand. I think there's a raise hand button, and I'll be able to see that and respond. Okay, so on Tuesday we finished up our discussion of the first type of transition metal reactivity here, which is simply a ligand substitution reaction. And today we're going to discuss intramolecular rearrangement reactions, and then we'll start to discuss electron transfer reactions. So intermolecular rearrangements can sometimes be referred to as stereochemical non-rigidity. And these are transition metal complexes that have reactivity of two different types. The first type is what's called fluxionality. And this is where you're swapping ligands on the transition metal, but the configurations that result from those swaps are equivalent. So an example that we'll cover will be exchanging axial and equatorial ligands for a trigonal bipyramidal transition metal complex. So here you don't have a change in the coordination geometry of the metal, but you're still able to swap ligands between positions. And then the second type of stereochemical non-rigidity is an isomerization reaction. And so this is an interconversion between chemically different configurations. So we'll see a couple of different types of this. The first will be interconversion between two different coordination geometries. Of course, this is without changing the composition of the transition metal complex. And the second will be interconversion between different ways in which a ligand is attached. And so these are called linkage isomers. And many of these reactions, either fluxional or isomerization reactions, have been studied by solution NMR spectroscopy. So a lot of our understanding of these reactions is from analysis of NMR spectra. And most of the reactions that have been studied have activation barriers that are in the range of 5 to 30 kilocalories per mole. And these are barriers that allow the interchange to be followed by NMR spectroscopy at readily accessible temperatures. And so this corresponds to rearrangement rates of 100 to 100,000 times per second at some accessible temperature. And that just means that at those rates, the NMR spectra can be collected faster than the reaction is occurring. All right, so our first example will be an isomerization reaction. So if you think about the coordination geometry of a nickel-2 complex, for a square planar geometry, we have a lot of examples where phosphine ligands surround the nickel-2 center. And electronically, square planar geometry is often preferred for 4-coordinate species. But if you have sterically encumbering ligands, such as bromide or iodide, then the nickel-2 prefers to be tetrahedral in geometry. So an interesting phenomenon arises if we have a mixture of these types of ligands. And so here, this is a complex where we have a somewhat sterically encumbering phosphine. So phosphine with an ethyl and 2 phenyl substituents. So we have 2 of those. And then 2 bromido ligands on nickel-2. And for that ligand set, the energy difference between nickel being tetrahedral in geometry versus square planar geometry is very small. They're roughly the same energy. So in solution, we have then an equilibrium between those 2 geometries. And that equilibrium can be monitored in a number of ways. But for example, these molecules, these different geometries have different colors, so different absorption spectra in the UV visible region. And the tetrahedral complex is green in color, whereas the square planar complex is brown. And so we can distinguish them spectroscopically, but also if we think about the electronic structure, the magnetic moment for these 2 different geometries should be different. So here's just from a simple crystal field model, we can see which is going to be the same situation in a molecular field approach or a molecular orbital approach. So here for the tetrahedral complex, a D8 configuration for nickel-2 gives rise to an S=1 ground state. But for the square planar geometry, we have an S=0 electron configuration with a large gap between the levels for dz squared and dx squared minus y squared based MOs. So this equilibrium can then also be probed by looking for signals from the spin of the molecule, and you can measure magnetic moments as a way of distinguishing. So here, the green tetrahedral form, as we said, is S=1. The brown square planar form is diamagnetic. And you can actually, depending on the crystallization conditions, you can sometimes crystallize the tetrahedral green form of the molecule. And under other conditions, sometimes you'll get the square planar brown form of the complex. And in other conditions, you might get a mixture of those 2 types of crystals forming from the solution. And so this speaks both solution probes and ways of crystallizing the molecule speak to the fact that these are very similar in energy and present at very similar amounts in solution. So as I said, solution spectra indicate the presence of a mixture of the 2 isomers. So here is a spectra. Here are some spectra for a very closely related compound. It's not quite the same, but it does a similar thing. And so the complex is shown at the top left. And in this case, the phosphines have methoxy aryl groups, 2 of those, and 1 methyl group. And also still, so 2 of those phosphine ligands, and again, 2 bromide ligands. And this molecule does very similar interconversion to the previous one. But here you're seeing spectra collected at different temperatures for a solution of that molecule in deuterated chloroform. And the top spectrum is at 30 degrees near room temperature. And at this high temperature, you see a single proton NMR spectrum for the molecule, meaning that the two geometries are rapidly interconverting. And so at this temperature, the conversion between those two geometries is faster than the time scale of collecting the spectra. And so you see an averaged spectrum, and it looks like there's just one type of the molecule present in solution. But if you start to cool this solution down at about minus 25 degrees C, you'll see that the spectra start to broaden, and this here you're seeing a intermediate spectrum where the two different the spectra for the two different geometries are starting to resolve. So at this time scale, the time scale of the NMR collection of data is very similar to the interconversion rate for the two geometries. And then at the bottom is a much lower temperature spectrum for minus 68 degrees C. And here you can see there are assignments for the two different resolved geometries. And in the designations here, T is representing the tetrahedral form of the complex, and P is representing the square planar form of the complex. And so you're seeing proton resonances for the molecule. And so the protons that you can find are the ortho and meta protons on the benzene ring, the protons on the methyl group of the methoxy substituent. And in the planar case, you can also find these protons attached to the phosphorus of the phosphine, right? You'll note that for the tetrahedral form of the molecule, there's no assignment for that methyl group, the one directly attached to the phosphorus. And this has to do with the effects of electron spin on these nuclear magnetic resonance experiments. So remember, for the tetrahedral complex, the spin is 1, so it's paramagnetic. And that spin, that electronic spin, will have an impact on the relaxation of the proton nuclei. And so what will happen in that case is you'll see proton resonances that are shifted to much further in field strength. And so you'll see peaks, for example, you can see for the tetrahedral complex, this peak for the meta proton on the benzene ring, protons on the benzene ring. This is shifted to very negative parts per million in the spectrum. And so that's due to its proximity to the spin of the metal center, right? And a peak like this proton on the methoxy group, which these are held further from the spin of the metal, these are going to be less shifted and less broadened in character in these spectra. So in part based on those spectral changes to the spin, these peaks can be assigned, and you can even quantify, for example, by integrating those methoxy proton resonances. We can quantify and see that these two forms of the molecule are present in very similar quantities. But as I said, the protons closest to the spin for the tetrahedral geometry, those are not observed in this spectrum. Okay, so this is how we can follow one of these reactions and understand how much of each is present in a mixture. So now let's move to a very common example of fluxionality, which is for trigonal bipyramidal complexes. Fluxionality here is going to be leading to exchange of axial and equatorial ligands. And so in a trigonal bipyramidal geometry, of course, you have distinct positions for the 3 equatorial ligand sites versus the 2 axial ligand sites. Those are chemically distinct. But if you measure under most conditions an NMR spectrum, you'll see that it's an average spectrum and you only see one type of ligand, right? Meaning that the axial and equatorial ligands all look the same. And that's because the activation barrier for swapping them is usually very small, just a few kilocalories per mole. So examples of this kind of fluxionality occur for example, with iron pentacarbonyl. So this is formerly an iron 0 trigonal bipyramidal complex. Cobalt pentamethyl isocyanide. So here we've got 5 methyl isocyanide ligands arranged in a trigonal bipyramid and bound to a cobalt 1 center. And then finally, importantly for understanding these molecules, is this example of a rhodium 1 phosphine complex. So here we've got 5 trimethoxyphosphine ligands, and it's also trigonal bipyramidal. And it turns out that the activation barrier for this rhodium 1 complex is higher than for most trigonal bipyramidal molecules. And that allowed some NMR studies to recognize that in this rearrangement, in this swapping of axial and equatorial ligands, by analyzing the line shape for the spectra, they could recognize that the process was involving simultaneous swapping of the 2 axial ligands for 2 equatorial ligands. So whatever mechanism this is proceeding through should be consistent with that observation. And the mechanism that is thought to be operational here is what's called a Berry pseudo-rotation mechanism. And in this mechanism, we're going to simultaneously move 4 of the ligands, and we're going to hold this left-hand ligand fixed. So this is, for example, iron pentacarbonyl. So here's the iron 0, carbon, oxygen. In this operation, we're going to do a couple of things. So we're starting with the D3H symmetry trigonal bipyramid with the unique 3-fold axis pointed vertically. And we're going to start to pinch the 2 axial ligands together towards each other, as shown with the green arrows. And at the same time, we're going to splay these 2 right-hand equatorial ligands away from each other. Again, as indicated by these green arrows, they're moving within the equatorial plane, the initial equatorial plane. And as you do those 2 motions, eventually you'll get to a C4V symmetry and a square pyramidal geometry. And this will be this motion will then continue. So we can continue pinching the axial, what were the axial ligands together, and splaying what were the equatorial ligands apart. And eventually you'll reach this geometry shown at the right. So here we're then back to a trigonal bipyramid. D3H symmetry, but you'll note now the 3-fold axis is going into the plane of the screen. And so these two ligands, the foremost and back carbonyl ligands, those are the axial ligands now, whereas originally they were equatorial. And these two ligands that were axial initially are now in these what are now equatorial positions. So if you look at the starting point and the product on the right, it looks like we've just taken and rotated the threefold axis by 90 degrees towards you. And so that's why it has the name of pseudo-rotation. This mechanism is thought to be operational, but it's something that's very difficult to prove. Actually, first, let's look at a movie. So here you're seeing this pseudo-rotation mechanism in action. And you can see sort of halfway between the two rest points is the square pyramidal C4b activated species. And so the energy of that species is what's giving rise to the activation barrier for interconverting between axial and equatorial ligands. And in iron pentacarbonyl, this happens very rapidly under most conditions, such that you see an averaging for spectra for the two different ligand types. Okay, so although the Berry pseudo-rotation is thought to be operational, there are other mechanisms which are difficult to rule out. There has been some experiments attempting to do this. It's difficult, of course, to prove a mechanism definitively. And for many years, really the only thing we had to rely on here were computational studies. And so there's a lot of computational work on probing different pathways that would be consistent with exchanging two axial for two equatorial ligands. And one of the more important other options for the mechanism was what's called a turnstile rotation mechanism. And the turnstile mechanism is operating just like a turnstile at, say, the BART station. When you go in, you know, the turnstile tends to have three prongs, and it rotates around a threefold axis. And so that's indicated here. The motion's indicated at the left. So in this complex, we've got two axial ligands, top and bottom, labeled A. Three equatorial ligands are labeled E. We're going to pick one triangular face of the trigonal bipyramid, and we're going to rotate that triangular face. And the rotation is indicated here with these arrows. And if you rotate it and move it slightly, you can get to the positioning shown at the right, where now what were equatorial ligands are axial. So the threefold axis is now, instead of vertical, it's horizontal. And these two, what were axial ligands, are in the equatorial plane. And so again, here we've swapped two axial for two equatorial ligands in this mechanism. So to probe this, if it's happening very rapidly and you can't probe it experimentally, you're left with trying to understand this mechanism through computational chemistry. And so here's just an early example of, you can see there are many, many papers on this subject in the 70s. And maybe one of the simplest molecules that does this interconversion is pH5. And so here you're seeing the results of calculations for the left panel in this plot. This is the Berry pseudo-rotation mechanism, BPR. And what you see is that there's a relatively small activation area for that mechanism, less than 2 kilocalories per mole calculated for doing the Berry pseudo-rotation. For the turnstile rotation, it turns out there are a number of ways in which you can do that. And it has to do with the tilt of the triangle relative to the other ligands as you do that turnstile rotation. And it's not important to go through them in detail, but here they analyzed 3 different modes for doing that sort of rotation. And the lowest activation energy was for what's designated mode 2. But you can see this is 10.4 kilocalories per mole. So 5 times, more than 5 times the barrier for the Berry pseudo-rotation. And so many such calculations have been done, including much higher level calculations than cited here. And all of them point to the Berry pseudo-rotation generally having a much lower activation barrier. And that has a lot to do with why it's the accepted mechanism for this rearrangement. Okay, any questions on what we covered so far? If so, go ahead and speak up. All right, if not, let's keep going. So now let's take let's consider another type of isomerization and recall Alfred Werner really made his name by showing that he could isolate 2 different enantiomers of an octahedral complex and that they were mirror images of one another through circular dichroism spectra. But for some of these tris chelate complexes, like Werner made, the 2 enantiomers actually interconvert. And if you go to a high enough temperature, you'll see that, or wait long enough, you'll see that the delta and lambda forms of these D3 molecules are interconverting. That was not the case for Werner. So the cobalt-3 complexes that he managed to resolve and show were mirror images, those are very slow and high barrier for interconversion. So that was important because he needed to be able to chemically resolve the 2 different enantiomers and take the spectra. And but there are other tris chelate complexes that can interconvert on reasonable timescales. And so this is a racemization reaction. You'll note that the starting geometry and the end geometry have the same stereochemistry. Well, so let me take that back. Lambda and delta isomers are stereochemically distinct, and so this would be an isomerization type of reaction. All right, so racemization of tris chelate complexes. Examples that have been well studied include tris ethylene diamine complex of nickel 2. BIPY is bipyridine. So this is, you've seen this before, but 3 bipyridine ligands. These are 2 pyridine groups that are connected through a carbon-carbon bond. This is a more rigid chelating ligand than ethylene diamine, right? Ethylene diamine has some conformational flexibility. And then the third example is this rhodium tris oxalate 3- complex. So oxalate is C2O4 2- ligand, which in some of the previous slides, you should be able to find the chemical structure. But again, it's a planar, more rigid ligand that's involved in making the chelate ring. So these 3 complexes actually can undergo racemization, interconversion between delta and lambda isomers, and those reactions have been followed, and they actually proceed through 3 different mechanisms. So one of the simplest ways of rearranging these is going to be by detaching one end of a chelating ligand, rearranging the other ligands, and then reattaching. So the ligand coming off, dissociating, and then reassociating. And that's something that some ligands can do, but other more rigid ligands might not be able to do. So bipyridine, for example, can't readily do that, whereas ethylene diamine can, and it turns out oxalate can. Another mechanism would be an entire chelating ligand comes off, so both metal ligand bonds dissociate. So that's the mechanism for bipyridine racemization. Entire rigid bipyridine ligand comes off and then comes back on to form the other enantiomer. And then the third method is going to be an intramolecular rearrangement where there's no detachment of any of the donor groups. And these, you can of course probe this via kinetics, and one important observable is whether or not the racemization is happening at a faster rate than the rate of ligand exchange, or the rate of detaching one end of a chelating ligand. And if that racemization is faster than a ligand dissociation event, then we must assume that the reaction is going through some intramolecular twist type of mechanism, where you're not releasing the coordination of any of the ligands. And so there have been a number of possible twist mechanisms to explain this kind of intramolecular rearrangement, where you're not dissociating any of the ligands. And this kind of twist mechanism is thought to be responsible for the racemization of nickel tris ethylene diamine 2+. Right? So that molecule is going to go through a twist mechanism. And the 2 mechanisms for twist that have been that are thought to be possible and have been considered are what's called a Balar twist and a Ray-Dutt twist. Well, first of all, here is the idea for a detachment mechanism. And this is what the oxalate complex uses to isomerize. So here, one end of the chelating ligand detaches and then moves to another position to form the other enantiomer. And the activation barrier could be dictated through either a trigonal bipyramid or square pyramid sort of intermediate geometry. Okay, so coming back to these twists where we don't rearrange or don't detach any of the chelating ligands. So we're going between delta on the left and lambda on the right. And in the middle, you see the Balar twist. And so here are we're going to twist around a C3 axis for the octahedral complex, and it's going to be the vertical axis as shown. And the red lines here, these are indicating the 2 coordination sites in the octahedral coordination sphere of the metal that a single chelating ligand is attached through. Right, so there's one chelating ligand here, here, and here. Now those are labeled 1, 2, and 3. And so we can twist the top triangle relative to the bottom triangle. And as you do that twist, you come to the trigonal prismatic intermediate or activated complex, right? And that's going to usually be high energy. And then if you continue that motion, you can get to this form of the molecule. And this is now the other enantiomer, the lambda enantiomer, right? So going back and forth, you have to go through this, whatever the energy here is for this trigonal prismatic geometry. And that means you're really putting a lot of strain in this chelating ligand for all three chelating ligands. Right? So that could be problematic. This is a lot of strain at all three chelating ligand sites. The bottom mechanism is corresponding then to the Ray-Dutt twist racemization mechanism. And here, instead of rotating around this vertical axis, we're going to rotate around a different threefold axis. And it's the one that penetrates this front left bottom triangle, and the threefold axis that goes through that, and also the triangle defined by positions 4, 5, and 6. Right. So we're going to instead rotate around that axis. And when you do that rotation, this left-hand chelating ring isn't going to go into this trigonal prismatic activated geometry, nor is the chelating ligand on the back triangle connecting 5 and 6. So here, only this foremost chelating ring is going to be strained, right? So the trigonal prismatic intermediate has strain associated with this edge, but the other two can adopt their normal relaxed conformation. And so you would expect, based on this, that the activation barrier for the Ray-Dutt twist should be significantly lower than for the Balar twist. And in fact, that's the commonly accepted mechanism. It's thought that most of these intramolecular racemization reactions occur through a Ray-Dutt twist type of mechanism, rather than the Balar twist, which would be higher activation energy. Okay, so particularly the Ray-Dutt twist. All right, any questions on racemization here? If so, speak up. If not, we'll move on. All right, so now finally, let's consider a very important type of stereochemical non-rigidity, which is the ligand changing the geometry of how it's bound to the metal. And this is what's called linkage isomerism, or linkage isomerism reaction. And it happens because some ligands are what's called ambidentate. They can bind to a metal center through more than one coordination mode. Some ligands actually have two different ways they could bind to a metal, but some, as we'll see, have many different ways they could coordinate to a metal center. One of the most commonly encountered examples, and historically a very important example, is this isomerism between a nitro coordinated NO2 minus and a nitrito coordinated NO2 minus ligand. So NO2 1 minus as a ligand, if it coordinates through the nitrogen atom, as shown at the left, we call that a nitro complex. If instead it coordinates through one of its oxygen atoms, we call that a nitrito complex. And so here, this is not a new idea. In fact, the possibility that such different isomers existed was first proposed by Sophus Mads Jorgensen back in 1893. So remember, Jorgensen was Werner's nemesis in counting isomers and the debate over coordination geometry versus Blomstrom's chain theory. Okay, so this is a particularly important example, and this interconversion for even particularly this molecule, it can happen in solution state, but it can also happen in the solid state. And the rates at which it happens and the fact that it can happen in solids at relatively fast rates where atoms tend to be rather localized and not able to undergo intermolecular reactions suggests that it's really an intramolecular process, and it's thought to proceed through what's called a nucleophilic internal displacement mechanism, which we'll take a look at shortly. Here is a table with some data for exactly this kind of rearrangement. And so here we're starting with the oxo-bound nitrido form and watching it isomerize either for the top part of the table in the solid state in a crystal of the solid, or at the bottom in solution, in aqueous solution. And you can see the sort of activation energies. In some of the solids, there are two different forms of the complex. So you see two different activation energies. But the thing to focus on is really K1 and EA, the measured EA1 values. But you can see the sort of energy involved for this rearrangement. And in the solid state, that leads to rate constants in the region of 10 to the minus 5 to 10 to the minus 7 per second. But in solution, as you'd imagine, these can happen more quickly. It's easier to move and change geometry in a solution environment compared to a more rigid solid environment. And so the reactions in the solution state happen at about 10 to 100 times faster, as you would expect, perhaps. And so these molecules actually have different infrared spectra, but also UV-Vis spectra. They're actually different colors for the two molecules. If we look at the infrared spectra, here you can see the solid line is the nitro form of the molecule. These are solid state spectra. And this is for the nitrogen bound to the cobalt is shown in the solid line. And this peak here to the right, that's the metal nitrogen stretching band for the molecule. And then the dashed spectrum corresponds to the nitrido form where oxygen has coordinated. And so here you see a peak at around a little below 1100 wave numbers corresponding to the metal oxygen stretch for the oxygen bound form of the ligand. And so these are very prominent spectral features that allow you to follow the course of the reaction. And this reaction happens thermally, but it can also be driven photochemically. If you hit this nitrido form of the compound with the right wavelength of light, it will convert to the nitro form. And if you hit it with a different wavelength of light, you can convert back. So these interconversions can be driven photochemically as well. Okay, so let's talk about the mechanism that's thought to be occurring. As I said, this occurs relatively rapidly in the solid state. And in solution, a lot of experiments have shown that it's actually just intramolecular mechanism. And so if we start with this nitrito form with oxygen bound to the metal, then this internal nucleophilic displacement reaction happens by this NO part of the molecule moving up and taking on a side-on interaction with the metal. So the nitrogen slips towards the metal and the oxygen slips up. And that gives us what's thought to be a transition state that looks like this, where we've got a side-on and interaction of both nitrogen and oxygen with the metal. And that motion of this upward rotation of the NO2 minus ligand continues until the nitrogen is actually coordinated to the cobalt. So importantly, throughout this process, you don't detach, you don't dissociate a ligand from cobalt, right? Remember, cobalt-3 here is inert, and it's going to be very slow to lose one of these ligands. And so one key observation is that this interconversion between linkage isomers is happening much faster than replacement or a substitution reaction on the complex. All right, so you can go back and forth between nitrogen and oxygen coordinated, and the oxonitrito form of the molecule is red, and the nitro form is yellow. So the one thing to think about here is how the electronic structure changes for the metal as you change the coordinated atom of an ambidentate ligand. And so here you can see some of the thinking and understanding how thiocyanate likes to bind. So thiocyanate can be either coordinated through the nitrogen end of the molecule or through the sulfur end of the molecule. And the nitrogen end has less of a steric encumbrance. So if you have bulky ligands on the metal, that will favor nitrogen coordination, right? The sulfur end is a softer coordinating atom compared to the nitrogen end of the ligand. So if you have a soft metal, then you might prefer sulfur coordination. If you have a hard metal, you might prefer nitrogen coordination. But just like we saw with other hard-soft considerations, the ligands on the metal, the other ligands on the metal, can influence the hard versus soft character of a given metal center. So depending on these other ligands, you might get a preference for nitrogen versus soft sulfur coordination. Right? And there can be solvent effects. So polar solvents versus non-polar solvents. Right? Okay, and of course, nitrogen versus sulfur is going to have a different molecular orbital interaction with the metal center. It's going to have some change to the MO diagram. Some ligands can be much more complex in how they coordinate. So SO2 is a nice example. Sulfur dioxide can coordinate in many different ways. So it can have this sort of planar geometry where the sulfur is attached, or it could be a pyramidal geometry with the sulfur attached, or it could be a side-on SO interaction, bidentate, similar to the intermediate we drew in the nitrito-nitro conversion. Or particularly for harder metals, you'll see oxygen coordinated. It can also bridge between two different metals. So here you see sulfur spanning two different metals. So examples of each of these coordination modes are given, and you should also think then in the different coordination modes, what is the nature of the ligand? So here, this coordination at the top, sulfur is a sigma donor and a pi donor. When it's pyramidalized, then the pi nature in particular is going to change the metal ligand interaction. Okay, and of course oxygen, it's a sigma donor, but as we've discussed, it can also be a pi donor type of ligand. Okay, any questions on linkage isomerism? If so, please speak up. All right, if not, then, oh, I see a raised hand.
Sorry, I have a question about the second pyramidal thing. So why is S predominantly as a sigma donor here and perhaps a pi acceptor?
Mm-hmm. Yeah, what's your question?
Oh, my question was that why is that the case? I don't get it.
Okay, well, so for the planar geometry, you're going to have a p orbital that's filled on the sulfur that could donate. You understand that interaction?
Yes.
But as you bend the oxygens down, you're going to lose that sort of pi interaction, and you're going to make a lone pair coming off here. And so the pi acceptor interaction, it's going to have to come from some excited, some higher energy orbital for the sulfur. It's going to be an anti-bonding orbital that's being stabilized and allowing access to an empty p orbital instead of that filled p orbital. And so that p orbital is going to be the one that's actually going into the plane of the screen here. And so that p orbital that has anti-bonding character with the oxygens, that is now going to actually be appropriate for a pi interaction and a pi accepting interaction with the metal.
Thank you.
Okay. Yeah, some of these are very complicated in terms of analyzing the electronic structure. All right. Okay, so in the remaining time, we're going to just start thinking about electron transfer reactions. And, you know, these are important for a lot of systems, including biological systems. And so we're going to spend, you know, several lectures understanding electron transfer reactions. They're important. They were important historically for developing our understanding of electronic structure of some complex materials and magnetism, the origins of magnetism, in addition to electronic structure theory. All right. So in the electron transfer reaction, of course, we're going to have an electron that's moving from one metal center to another. And so that reaction has, of course, a free energy associated with it. And you know, so deciding whether or not that electron transfer will occur is something that we do using standard reduction potentials. And so I think you've been introduced to these in your general chemistry class. But this formula here shows how to calculate the Gibbs free energy from those standard reduction potentials by using this Faraday constant and the number of electrons transferred. It's the negative of that value. So this is true under, this expression works under standard conditions. And so you can look up, as we'll see in the following tables, you can look up these standard reduction potentials, calculate them from half reactions. And this Faraday is just converting from electron volts to kcals per mole. And this is going to be the number of electrons transferred between the molecules. Right, so these are numbers we can look up, or if they're new species, then we can measure them electrochemically. And in general, we're going to be concerned with what's the specific mechanism for such a reaction where an electron transfers from one metal center to another. And there will be two types that we'll consider in detail. The first is what's called an inner sphere electron transfer reaction, and this proceeds through formation of a bridged intermediate. So you're going to have one or more atoms covalently connecting the metal centers, and then the electron can transfer usually through that bridge. And so this is a complicated electron transfer reaction because it also will involve ligand substitution as part of the reaction. And then the second way this type of reaction can happen is through an outer sphere reaction. And here you don't form a covalent bridge. Rather, the two metal complexes will diffuse together, and when they're in proximity, then the electron will jump from one metal to the other without involving any intermediate covalent bridge formation. So both of these are important depending on the molecule. In some reactions, both are going on simultaneously and just have different rates. Okay, so you have these are for reference and for you to study, but here are a couple of lists of half equations for giving reduction potentials for a variety of reactions, simple reactions involving mainly transition metals. And so here are where you would take these E naught values from. So any inorganic textbook will generally have tables of these, and there are even more extensive compilations that you can find. And again, if you don't have these, you can do a electrochemical measurement to determine them. Okay, so let's consider some examples of these two different reaction types. And the first, let's consider an inner sphere what's thought to be an inner sphere electron transfer reaction, which happens between chromium-2 hexaaquo complex and a cobalt-3 pentaammonia chloro complex in acidic aqueous solution. So the acid here is going to it's going to protonate the amine groups ultimately, and the product that you eventually get from this reaction, the products that you get are chromium-3 with 5 water ligands and 1 chloride ligand now. So we've changed and replaced one of the waters with a chloride, and we've transferred an electron from chromium-2 to cobalt-3 to form chromium-3 and cobalt-2. Right, so this is formally transferring electron from chromium-2 to cobalt-3, forming chromium-3 and cobalt-2. But at the same time, we've had ligand substitutions going on. So the first substitution is we've substituted a chloride for a water, but then cobalt-2 has completely lost all of its ligands to form the hexaaquo complex, and now we have the 5 amines released into solution form ammonium cation. Right? So this is consistent. You'll note that in this reaction, we've got a labile species, an inert species with a chloride ligand that could form a bridge to the chromium. And in our products, the chromium-3 is inert. And so it's hanging on to that chloride once we form the bridge. And that's leading to this change in the ligand set. And then for the cobalt-2, once we transfer the electron, cobalt-3 is inert. It can hang on to these ligands in acidic aqueous solution due to its inertness, its kinetic inertness. But if we transfer the electron and form cobalt-2, cobalt-2 is labile and it rapidly loses its ligands, and those are replaced with water. Okay, so next, let's compare that with an example of an outer sphere electron. So an example here is ferrocyanide, FeCN6 4-, reacts with hexachloroiridium 3+, so iridium 3, overall charge state is 3-. So this reaction is thought to happen via an outer sphere mechanism. These two molecules diffuse together. An electron transfers from iron 2. So this is iron 2 on the left and iridium 3+. And we're then making iron 3 and iridium 2. Right? So an electron's transferring from iron to iridium in this reaction. And they don't change ligand sets. And that happens because these are inert species. So substitution in this low spin hexacyano complex of iron 2 is extremely slow. Ligand substitutions of those cyano groups are very slow. Iridium 3, of course, is inert. And so, but this electron transfer happens at a much faster rate than those ligands would exchange on those metals. Another example is shown here, and this is again chromium-2 reducing cobalt-3 in aqueous acid. But in this case, we don't have a chloride ligand on the cobalt-3 center. And if you don't have a chloride ligand, then you don't have a good bridge forming species. Ammonia is not capable of forming a covalent bridge connecting cobalt and chromium. And of course, chromium-2 is labile, cobalt-3 is inert. So they're going to diffuse together. And once the electron transfers, you form cobalt-2, then cobalt-2 will lose the ligands and you'll form the hexaquo complex. So the difference here is the top reaction has to go outer sphere mechanism because ligand substitutions are much slower than the reaction is happening under. And the bottom is there's no good way of forming a bridge. We don't have a good bridge forming ligand, and therefore it must be going through an outer sphere mechanism. Right? And so a general statement here is if electron transfer proceeds faster than ligand substitution, then the reaction is going through an outer sphere pathway. Okay, we're going to go through this in much greater detail and analyze the mechanisms. So this will become even more clear as we proceed. All right, so for the last part of lecture, I want to talk a little bit about a really classic piece of chemistry that relates to our understanding and was instrumental in helping and aiding our understanding of electron transfer reactions. And it's a piece of work that was done by Carol Kreutz when she was a graduate student with Henry Taube at Stanford. And she was a really exceptional student who made one of the most famous molecules in inorganic chemistry, which is now known as the Kreutz-Taube ion. So she synthesized this and characterized its really unusual spectral properties, but also recognized that this was a new type of molecule which had an internal electron transfer reaction going on, and that these understanding of the electronic structure could come from interpretation of the absorption spectra. So Carol Kreutz had a very long and distinguished career in chemistry. In particular, she spent most of her career at Brookhaven National Lab. This is a Department of Energy lab, and there she was director of the chemistry division for many, many years, leading a team of more than 100 scientists. So the paper that we'll discuss is this one in JACS from 1969. This is a classic paper in inorganic chemistry. We've uploaded it to the B Courses website, and it's very short. I encourage you to read it. But the title is A Direct Approach to Measuring the Frank-Condon Barrier to Electron Transfer Between Metal Ions. And this is just going to be an example molecule to think about as we proceed through the next few lectures and think about electron transfer mechanisms. And I want to point out, this is going to be an example of a molecule where it's clearly an inner sphere electron transfer process. You have two metals in the molecule, and the electron can go back and forth through a bridging pyrazine ligand. So pyrazine is this form of benzene where you've replaced two opposing CH bonds with nitrogen, and those two nitrogen atoms can coordinate to a metal. And so in the beginning of this paper, they say that this species has been characterized. And so here we've got ruthenium. So note the overall charge is 2+. So this is ruthenium 2. It's an octahedral geometry with 5 ammonia ligands and then 1 pyrazine ligand, a terminal pyrazine. Right? And so they say this molecule has previously been synthesized, and it shows a band with the maximum at 472. These units of millimicrons are archaic. That's just another, so a millimicron, 1,000th of a micron is a nanometer. So this is a band at 472 nanometers in the visible region of the spectrum. And that peak is attributed to a charge transfer absorption from a metal T2G electron. Remember, ruthenium-2 here is it's octahedral coordination. It's got a T2G6 electron configuration. It's pseudo-octahedral, but we'll consider it octahedral for these purposes. So T2G6, low spin D6 electron configuration. And so this band has been assigned to an electron being promoted from ruthenium T2G orbital into the pi star orbital of pyrazine. Right? And then they add this species, again, ruthenium-2 with 5 ammonias, but with a water ligand instead of pyrazine. And if you add those two molecules together, you start to get a new band developing at 547 nanometers. And they used a sort of titration method known as Jobs method to determine the stoichiometry of the complex. So this is basically just fixing the amount of ruthenium present, but varying the amount of pyrazine versus aquo complex. And you get a maximum in the absorbance of this spectral feature when you have a 1-to-1 ratio of the molecules. And that's taken as evidence that you're forming then a new molecule that has 2 rutheniums for each pyrazine ligand. Right? So those, what's called job plots, or the Jobs method, is indicating formation of this species labeled 2. So here we've got 2 metals now on the pyrazine, and still ruthenium 2+, ruthenium 2+, and a 4+ overall charge. So that's quite an elegant, simple bridged two metal complex. And so then they were particularly interested in what happens when you oxidize that molecule. And particularly what happens when you oxidize it by just one electron. So you can imagine if you take out one electron here, you're going to be removing it from one of the ruthenium-2 centers. So normally you would think of this as you're going to form one of the metals will be ruthenium-2+, one will be ruthenium-3+. We should point out in this molecule 2 here, these two ruthenium centers are equivalent by symmetry. They have the same ligand set, the same geometry, the same electron count. They're indistinguishable in this molecule. And when we oxidize one of them, you have a situation where you have the same coordination environment, just in a different valence electron count for the two rutheniums. One's ruthenium-2+, one's ruthenium-3+. And the interesting thing about this molecule 4 here is that electron or hole, so when we oxidize, we've got a hole. That hole can hop between the two ruthenium centers. Or analogously, the electron and the position of ruthenium-2 can hop between ruthenium centers. And so one of the really fascinating features of this molecule is that it led to a huge debate of whether ruthenium in this complex consists of one ruthenium-2 site, one ruthenium-3 site, or if the molecule is better described as having equivalent ruthenium sites, each of which is ruthenium plus 2.5 oxidation state, right? And so this was just making that molecule, which led to a huge amount of science trying to understand that, and we'll talk more about that later. They then, so they're able to see this species and even isolate it. Here, this is the tosylate salt. Actually, so don't worry about this. This is just an anion that's balancing the 5+ charge. It's called tosylate. But here we have the two rutheniums bridging as shown in structure 4. Okay, so the interesting thing that Kreutz and Taube observed for this 5+ form of the molecule is it shows a new intense absorption band in the near infrared region of the spectrum. Okay, and so again, millimicrons is just nanometers. So this is out at about past 1600 nanometers, this maximum for this peak. The solid line here is for the 5+ complex, where you would have what's called a mixed valence, ruthenium-2+ for one metal and ruthenium-3+ for another, potentially. And then the dashed lines is just showing that you don't have any absorption feature in this region if you have the 4+ cation or the 6+ cation. So 4+ cation would correspond to both ruthenium centers being ruthenium-2, so not mixed valence. And the 6+ cation would correspond to both of them being ruthenium-3, and again, not mixed valence. And so the nature of this band is it's what's called an intervalence charge transfer band. And so you can think of it as arising from the transfer of an electron from ruthenium-2 to ruthenium-3. And the energy here, as they point out in this paper, is actually a measure of what's called the Franck-Condon barrier for this electron transfer reaction. So the Franck-Condon principle is really based on the observation that nuclei move much more slowly than electrons. And so this barrier is associated with the nuclei around each metal center getting into the right position for a charge transfer to suddenly occur to create an excited state of the product complex. All right, so what I just said is somewhat complicated. If you didn't follow it, don't worry. We're going to go through it in great detail in subsequent lectures. But this paper by Kreutz and Talby is really the main point I want to make here, is that this is the first, one of the key papers in recognizing that we could spectroscopically measure via such molecules these barriers to electron transfer. And in this case, it's going to be for an inner sphere electron transfer type of reaction. And so that energy is associated with, as you'll see, it's associated with 4 times the activation barrier for the reaction. And this is consistent with a theory put forth by a fellow named Rudolf Marcus. And we'll talk about his theory, Marcus theory, in a bit of detail later in the course. But the energy of that transition is allowing us to measure a very specific energy associated with electron transfer. Okay, so we're going to stop there. We have time for one question if anybody has an urgent one. Okay, if not, we're out of time, and we'll pick up there on Tuesday. Okay, bye.